Universidad de Sao Paulo. Tiene postdoctorado en Morelia, México y Barcelona. Su área de interés es topología general y teoría de continuos. En esta oportunidad el título de su conferencia es Six Matters, a Brief Introduction to Set Theoretic Topology. Sin más preámbulo, adelante, doctor Samuel Gómez da Silva.
Ok. Gracias por la invitación. En realidad es teoría de conjuntos, ¿no? Es topología general y teoría de conjuntos. Y bueno, muchas gracias por la invitación. Y desafortunadamente no soy fluyente para hablar de matemáticas en castellano. Así que voy a pasar a inglés, pero creo que al final para preguntas sí que puedo manejar en castellano, ¿sí? Entonces, perdón por cambiar a inglés. Well, this promise in the title to be a introduction to set theoretic topology, right? So I found the Wikipedia definition, and it's a perfect explanation we could expect from a mathematician in a certain joke I usually tell my students here in Brazil. You may see in the screen. In mathematics, set theoretic topology is a subject that combines set theory and general topology. It's a perfect and correct explanation, but gives no information whatsoever. There's nothing new. There's nothing new in this phrase, right? I looked for some classical books. These are classical books from the 70s and the 80s. To the left, we have the handbook of set theoretic topology. And to the right, the set theoretic topology is a collection of papers. And in both books, you will not find a definition of what would be set theoretic topology. They assume the area is well established and go from this assumption, right? But I believe that 90% of the people have no idea of what set theoretic topology is. I don't think it's a so well-established area, so one would not need to define them in some way, right? And then I find a good definition at this Reddit site. I don't know who is aware of the existence of this Reddit service, this Reddit platform. It's a place where people ask for questions, right? Ask questions. And this Orbital 1337 guy was answering this, how foundational is set theoretic topology? And he gave a pretty good, in my opinion, answer. Let's see the answer. And my comment, someone has thought that size matters before myself, right? So it's not defining set theoretic topology, but what a set theoretic topologist does, right? So a set theoretic topology might be interested in the cardinal invariance of a certain topological space. A cardinal invariance is essentially the size of some special set associated with the space. The simplest cardinal invariant would be the size of the whole space, right? In order to determine these invariants, one might use tools from infinitary combinatorics, which is an important area of set theory. One can also show that the values of certain invariants are not uniquely determined by ZFC, using methods commonly used in set theory to show independence results, especially forcing. Right? Disclaimer, in this talk, all emphases are mine. Wherever there is emphasis, it's from myself, okay? Well, this is how I know about Orbital 1337. Don't know who he is, don't know if he's a mathematician or a computer science scientist, I don't know. But it's pretty sympathetic, nice guy, you know? I praise for him. Well, some definitions I may properly quote. This is a definition from a 1984 lecture delivered at Amsterdam by this Dutch set theoretic topologist, Jan van Meel. It's a great set theoretic topologist. Well, set theoretic topology is that part of topology that uses results and techniques from set theory in order to solve its problems. In this field, set theory and topology walk hand in hand. This is, I think, it's very cute, hand in hand. Hand in hand. Set theoretic topology has been quite vital for the last 20 years. In 1984, it's from the 60s to the 80s, and has solved major problems. Mathematicians involved in this area are primarily set theorists who enjoy doing applied set theory, guilty as charged, and general topologists who solve their problems by working the well-known models of set theory, where axiom as V equals to L, Martin's axiom plus the negation of continuum hypothesis, the continuum hypothesis, or diamond hole. These are combinatorial statements largely known for set theorists. Right now, there's a growing number in the 80s. Right now, there's a growing number of general topologists, however, that try to construct their own models instead of making the set theories prove the consistency results they need. So this is a very good definition by John Lemieux in the 80s. And more recently, in a workshop held at Oaxaca, the beautiful city of Oaxaca, other first-class set theoretic topologies that were in the organization, including Alan Dow and Michael Grusek, had come out with some inspiring yet concise words about set theoretic topology, talking about topology in the view of a set theorist. Inspiration and testing ground. Topology has for decades served both as a source of inspiration and a testing ground for novel set theoretic techniques and axioms. I think this is very nice to have in mind. Well, let us stick to the basics. This is an introductory talk, so I will not strongly use the language of cardinal functions. Those cardinal functions are pretty much the cardinal invariants that sympathetic orbital 1337 has mentioned. And we avoid general statements in the language of cardinal functions by considering only the countable cases, or at least the countable related cases. We will understand what I mean by countable related. So, in fact, we will be between Aleph 0 and 2 to Aleph 0. There are cardinals related to Aleph 0 itself, and 2 to Aleph 0, right? So, in terms of topology, I will assume that everyone knows the basic separation axioms as T1, T2, T3, T2 Hausdorff spaces, T3 regular spaces, and we assume that T3 implies T1, okay? So the T3 spaces are regular spaces, regular Hausdorff spaces. And we'll use freely as well the countability axioms, right? The first, a space is said to be first countable if each point has a countable local base. This happens for all metric space, right? The second axiom of countability, space has a countable base if it has a countable base. That's a tautology alert. Well, I could say that a space satisfies the second axiom of countability if it has a countable base, but usually we say that space has a countable base, and that's fine, that's okay. And the third axiom of countability, a space is separable if it has a countable dense subset, right? These properties, which are taught by us in the introductory topology courses, these are examples of the first cardinal functions one could expect to learn. The first axiom of countability relates to the character of the space, this key of X, which is the minimum size of the local basis of the space. in fact, the supremum of the minimum size of the local basis for each point. The weight is W of X would be the minimal size of a base of the space, a base of open set of the space. The minimal has the size of the weight of the space, and the density P of X is the minimal size of a countable. It's the minimal size of a dense set, right? So the countable cases, if D of X is Lf0, the space is separable. If W of X is Lf0, the space has a countable base. And the countable character, the character Lf0, refers to first countable spaces, right? Other two countable topological properties, which corresponds to countable cases of well-known cardinal functions, and here we are starting to talk about Lindelof spaces with point G delta. It's something will be important in the contest by the end of the talk. Well, Lindelof is a property everyone knows. A space is Lindelof if every open cover has a countable subcover, right? And a space has all point G delta if it has all point G delta, meaning that all singletons, we refer to the points, but we are in fact talking about the singletons. If all singletons may be written as a countable intersection of open sets. Again, this is a property that metric spaces have, right? The cardinal functions relate to these properties for which those properties corresponds to the value Lf0, right, are the Lindelof degree, L of X, which would be the smallest cardinal kappa for which every open cover has a subcover not larger than kappa. And the pseudo character of X relates to the minimal size for which each point may be written as an intersection of a pseudo base. When the family of open sets, the intersection of the family is the singleton of a point, we call this family a pseudo base of the point. And the existence of pseudo bases for every point is in fact a characterization of T1 spaces, right? That's why I say that for T1 spaces only for contests. Okay, having our point G delta is strictly weaker than first countability. Here goes an exercise for the student presence. You may check the box, not the Tikhonov, the box. The box product of countably infinite copies of the real line. This space is not first countable, but all points are G delta, right? Alive and kicking, what I mean, besides that I'm a person which likes rock from the 80s, right? Alive and kicking. If you like these phrases, the values of certain invariants are not uniquely determined by ZFC using methods common. The values of certain cardinal invariants are not uniquely determined by methods to show independence results, especially forcing and general topology construct their own models for consistency. I would refer to the work of the Brazilian female set theoretic topologist, Lúcia Junqueira. I have to talk about Lúcia Junqueira because she was my PhD advisor, so I'm in debt forever to Lúcia. Well, this is my second year talking in the conference. I may talk next year as well if you invite me, but you could consider to invite Lúcia to talk. She's a brilliant mathematician in the field. Okay. And for cardinal functions, which would be generalizations for other cardinals of Lindelof degree, pseudo character, weight character, these cardinal functions, and many more. And inequalities as the ones we will discuss by the end of the talk. There are lots of researchers doing work right now about this kind of inequalities, so to say. And I may refer to the Brazilian researcher Leandro Auric, which is my brother. We were both advised by Lúcia Junqueira. And we have this Italian researcher, Santi Spadaro, who is fluent in both Spanish and Portuguese, has lived in Brazil for a number of years. So you may also consider to invite Leandro Auric and Santi Spadaro to give talks at this conference. Leandro was the advisor of Gabriel Wasmat Medina. You all that may know Gabriel, right? So I can tell you seriously, the type of math I am presenting you does not belong to museums. This is not museum material. This research is alive and very active, right? Well, I have to talk about certain basic stuff. So things we care more about than people from other areas of research. We work a lot with ordinals, the transitive sets well ordered by the membership, right? What is a transitive size? Elements of the elements are elements, right? This is a transitive set. And ordinals, where the membership is a well order, a linear order where also non-empty subset has a minimum, right? Those would be the canonical representatives of our well orderings. Every well order of a set is isomorphic to a unique ordinal, which is the order type, right? A set may be well ordered if and only if it may be indexed by an ordinal. So when we work with the under the axiom of choice, we are free to index every set by ordinals, right? The class of ordinal is the SPI, is the backbone of the universe of sets. Ordinals are denoted by lowercase Greek letters, alpha, beta, gamma, delta, zeta, epsilon. And the order on the ordinals is membership. So when we write that delta is less than zeta, we mean that delta is an element of zeta, right? And the same way happens for von Neumann natural numbers, for which 0 is the empty set, 1 is the set which has only the empty set. So 1 has only 0 as an element. 2 has precisely 0 and 1 as an element. So that n has precisely n elements, which goes from 0 to n minus 1, right? I have this joke with my students in that theory. Us at theories, we don't count for 1 to n. We count for 0 to n minus 1. Sorry. So as it happens for natural numbers, any ordinal corresponds to the set of ordinals below them. So that the ordinal alpha is precisely the set of all ordinals beta, which are less than alpha, and less than is the membership relation, right? Cardinals are the initial ordinals, are the first ordinals with a certain size, so to say, and size is given by bijective functions. So an ordinal sigma is a cardinal if and only if for every alpha below sigma, you have that alpha is not equipotent to sigma. There is no bijection between alpha and sigma. And cardinals are usually denoted by kappa, lambda, theta, and mi, right? And if you have a set that is well ordered, so under the axiom of choice, every set, right? Given a well-ordered set X, the cardinality of X would be the minimal ordinal for which there is a bijection between the ordinal and the set. Notice that as we are assuming that the set has a well-ordering, so it has that order type, that ordinal I mentioned a few minutes ago, right? So given a set, you have the order type of the set of under a certain well order. This ensures that it's a set. As it's written, you could talk that it's a class, but it's a set. This set is non-empty, so has a minimal element, right? And obviously, cardinals coincide with their cardinalities, right? That's a shorter definition of ordinal is a cardinal if it coincides with its cardinality. And under the axiom of choice, all sets have cardinalities defined in this way because of the well-ordering theorem, which is equivalent to the axiom of choice. So all cardinalities are cardinals. In Zermelo-Frankel without choice, the F is not so easy to define and work with cardinalities. This is something I will not go further. It's a pretty awkward situation. But for those who are interested, you have to learn about Scott Strick. In the 50s and 60s, Scott has defined a way to give the cardinality of a set, even in the absence of the axiom of choice. But it's not a simple situation to work. One may easily show that for well-ordered cardinals or the alephs, you have that kappa times kappa is equipotent to kappa, right? And in fact, this is pretty related to the axiom of choice because Tarski has shown that the axiom of choice is equivalent to the square of any set. The square of any infinite set is equipotent to set itself, right? So under Schroeder-Bernstein-Cantor theorem, which is the theorem that ensures that if there are injective functions in both directions, two sets are equipotent, right? This is what I said is a pretty obviousness under the axiom of choice. So the Schroeder-Bernstein-Cantor theorem is something that only has some interest if we consider only Zermelo-Frankel, right? So using this kind of argument, we have the well-known absorption law of cardinal arithmetic that when you consider the sum of two cardinal numbers, the sum of the two infinite cardinals, which correspond to the cardinality of a disjoint union of sets of each size, right? Or when you consider the product of two cardinals, which correspond to the size of the Cartesian product, why is absorption law? Because the larger is the winner. The larger will win here. So kappa plus lambda and kappa times lambda is the maximum cardinal, right? This is well known. Using the axiom of choice in a not so obvious way, we have the generalization of the mantra we tell the students that the countable union of countable sets is a countable set. In fact, for any union, you have this upper bound for the cardinality, which is given by the cardinality of the size of the family. So we have here the cardinality of the union of xy for I and I, right? So this is bounded above by this upper bound, which is the maximum because the product is maximum, giving at least one of them infinity, of course. It's this comparison of the size of the family and the supremum cardinality of the members of the family, right? And again, on unions, it's very important that when you consider a family, inside a set, we use the word family when we want to be popular or when we are giving us set theories. I'm speaking right now. We talk about families when we give topology classes or algebra classes or analysis classes. We know that everything is a set in set theory, right? So when you consider the union of a set of ordinals, which is a bounded collection of ordinals, no more than this. You in the union you sweep all elements beyond every ordinal of the family, and it's easy to see, or trust me on this for today, that whenever X is a set of ordinals, the supremum is also an ordinal, and furthermore, the supremum is precisely the union of the family of ordinals, the union of the set of ordinals, right? So the supremum for sets of ordinals coincides with the union, right? I and my circumstance. This is this world famous quote of this philosopher Ortega and Gasset, because we have two things that, depending on the situation, we use one name or other name, which is, to start with, the set of all natural numbers, which are precisely the finite ordinals, is given by the axiom of infinity if you studied axiomatic set theory. The set of all natural numbers is the first infinite ordinal and is also the first infinite cardinal, and it's denoted by omega, which is equal to Aleph zero, right? For us, when we write this natural number, as usual, is the naive set of natural numbers. When we write this way, we are not thinking about the axiom which give rise to the sets. This is pretty naive, right? The tendency is that a set theorist will talk about omega, not about n, right? So I and my circumstance, it's the same guy. It's the set of natural numbers. But when we want to talk about the set, for instance, to use it as an index set, to index a countable set, we write omega. And we want to talk about the cardinal, we write Aleph zero. But it's the same mathematical object. It's the same guy. By Cantor's theorem, we know that kappa is strictly less than the size of the power set of kappa for every kappa. In particular, there are as many real numbers as there are subsets of the natural numbers. So when we say that the cardinality of R is strictly larger than Aleph zero, we are giving a particular case of Cantor's theorem. So this the first information that there are uncountable cardinals, right? There are these infinities of different sizes. The same way that the first infinite ordinal is the set of finite ordinals, we also have the set of all countable ordinals. You may think of all possible orderings of subsets of the naturals. That's precisely it. Take all subsets of the naturals and give them wherever the well order you want. It's not only the usual. All order types of all possible well orderings of all countable of all subsets of the natural numbers will give you the set of all countable ordinals, and it will be the first uncountable ordinal, which is also the first uncountable cardinal. It's the first ordinal which surpasses omega in size, right? And this guy is omega 1, which is Aleph 1, right? And I and my circumstance applies again when we want to talk about the ordinal or when we want to index a set of size Aleph 1, we use the ordinal omega 1, right? To prepare you for the notation you will see in some minutes. Well, we have talked about Aleph 0, we have talked about the Aleph 1. Another crucial cardinal is 2 to Aleph 0, the cardinality of the continuum. C, this Gothic German C, right? In general cardinal exponentiation, kappa to lambda is the cardinality of functions of lambda to kappa, right? Where this lambda to kappa is the set of all functions from lambda to kappa. And well, in terms of size, real numbers and subset of natural numbers is the same for us set theorists, and subset of natural numbers is the same of infinite sequences of zeros and ones. So the size of R is the size of n to 2, and this is 2 to Aleph 0, right? So the size of R is the continuum. This is the noblest small cardinal. We say that small cardinals are cardinals which are somehow related to the set of all natural numbers. Worked a lot about small cardinals in my life, but I wanted to talk about basic things today. And well, it is independent of the usual axioms of set theory, where the continual hypothesis CH holds or not, where the continual hypothesis precisely to say that the first incountable cardinal would be the size of the real line. Thinking as Cantor would think, how Cantor stated the continual hypothesis in terms of subsets of the real numbers, right? So the continual hypothesis says that there are no sets with intermediate size in the real line. Under the continual hypothesis, given an infinite subset of the real line, either is equipotent to the natural numbers or is equipotent to the full line, to the full real line. So that's the continual hypothesis as stated by Cantor. Right. And I had proved in my career some topological equivalents from both the axiom of choice and the continual hypothesis. This concepts active research as well, but let us not touch this today. Well, things that a set theorists are more aware than the average of the mathematicians. If you take any kappa between 2 and lambda is an infinite cardinal, then 2 to the lambda, which is the size of the subsets of lambda, right? 2 to the lambda is equal to kappa to the lambda equals to lambda to the lambda, right? We have these brackets notation for subsets of a certain size. So if you have lambda not larger than the size of a set A, you may be interested in these brackets of A lambda, which would be the family of all subsets whose size is precisely lambda, right? Or brackets of A not larger than lambda would be the subsets of A whose size is not larger than lambda. And this is pretty easy to remember the value. Whenever you have an infinite set and a cardinal, you have these last equalities, the number of subsets of size lambda of the set A is equal to cardinality of A to the lambda. That's a simple thing to do in a basic set theory course, right? When you have the operations, the arithmetic operations under numbers appear also for infinite numbers, right? So 2 to Aleph 0 to Aleph 0 is 2 to Aleph 0 times Aleph 0. This is 2 to Aleph 0. And this is Aleph 0 to Aleph 0. So, for instance, there are as many sequences of real numbers as there are real numbers, because these would be 2 to Aleph 0 to Aleph 0. There are as many countably infinite sets of real numbers as there are real numbers, because this would be cardinality of the family of R not larger than Aleph 0, 2 to Aleph 0 to Aleph 0 again. There are as many infinite subsets of the natural numbers as there are real numbers, right? It's easy to realize that the finite subsets of natural numbers, a countable set, this is easy to achieve, right? Yes, so in fact, the weight, so to say, of the power set of omega is given by the infinite subsets. This is pretty. This is not a surprise if you studied a little of set theory, right? And this particular detail that 2 to aleph 0, 2 aleph 0 is again 2 to aleph 0 will be the great countable related case. I have talked about countable related cases, right? Here is what appeared. Well, we talk about things that are well known, things that we set theorists are more aware than people, but a thing that most likely will be known only by us set theorists is about the regularity of the ordinal omega 1 of the cardinal electron, right? Omega 1 is regular, which means that any countable sequences of ordinals in omega 1, and omega 1 is the home of all countable ordinals, right? It's the set of all countable ordinals. Any countable sequences of ordinals in omega 1 has to be bounded in omega 1. You can't achieve the first incountable ordinal through omega steps. You won't get that. We call that omega 1 is set of all countable ordinals, that the supremum is equal to union, and that with the axiom of choice, the countable union of countable set is a countable set, right? So if you have any function which goes from naturals to omega 1, there's the supremum. You won't be able to go cofinal function from omega to omega 1 does not exist under the axiom of choice, right? And in fact, the same happens for any zeta less than omega 1, because if zeta is less than omega 1, it's a countable ordinal. So again, you apply the combinatorial argument. You will get to a countable sequence, a countable union of countable set. It will be countable, so it will not be the whole omega 1, right? And facts which follow from the regularity of omega 1, I leave this as an exercise to the students mostly. If you get an increasing sequence, but not ordered by the naturals, but ordered by omega 1, right? An increasing sequences of omega 1 closed sets in a first countable space, you will have that this union is closed as well, right? As you are in a first countable space, you may think of each point in the closure of the set will have a convergent sequence going to this limit point. And you think now about the countable base, you may assume the countable base is decreasing. You will have points of F alpha 1, F alpha 2, F alpha 3, all of them will be elements of the greatest countable ordinal you consider, of the ordinals you consider, right? So it will be in the closure of the closed set, it will be in the closed set, right? And this is interesting as well. If you have a countable set, any countable set, and you have this countable set included in a union of omega 1 sets, this union need not to be supposed increasing, then you don't need of all these omega 1 sets to give your countable set a home. There will be a countable ordinal beta for which A is included in these X alpha for alpha less than beta, right? These some exercises for you. Well, things every mathematician should know about: transfinite induction. Induction may be done over every well-ordered set, or every ordinal zeta, not only over omega, which is the finite induction. And in fact, another homework for the students, It's much faster to work with transference induction than Zorn's lemma for maximality arguments, right? Check, this is the homework, check that for all properties that are preserved by unions of chains, such as being in a ring, being a linearly independent subset in a vector space, or being a chain in a family of sets, there is a straightforward recipe for a transference induction argument giving a maximal element in each structure with that property, right? So we don't know why Jordan's lemma has done so much success among mathematicians. How it could be done with transfinite induction. And well, the first transfinite induction was an argument using trees. We regard the Cantor set as family of branches of a countably infinite poset of closed intervals. We think as of the branches are the survivors in the Cantor construction. And mimicking such construction, we may prove that any perfect set of the real line with a closed set which knows isolated points includes a homeomorphic copy of Cantor set and thus has size C. And Cantor proceeded with the very first transfinite induction of the history of mathematics when starting with uncountable closed set F, this would be the F0, has iterated using ordinals the operation of taking cluster points, and after countable stage zeta, with zeta being possibly larger than omega, right? Countable but larger than omega, he has reached a fixed point, P, which would be F zeta or the cluster points of F zeta, and this will be a perfect set. All points are accumulation points. So this gives rise to the Cantor-Bendix theorem, because separable metric spaces are countable, and then discrete subsets are countable as well. So given an uncountable closed subset of the real line of, or even of any Polish space, is a separable, completely metrizable topological space, this uncountable closed subset may be decomposed into a countable set S and a perfect set P, right? This is Cantor-Bendixson theorem, and it's the beginning of set theory, as we know today, right? And how a set theory sees this? This in particular, as every uncountable closed set includes a copy of the Cantor set, it has to be size C, right? This ensures that a possible counter example for the continuum hypothesis that would be an infinite uncountable set, which is not equipotent to real line itself. Such a counterexample cannot be a closed set because the closed uncountable sets goes to the bottom. So the continuum hypothesis is true for closed sets. That essentially for sets that we are able to describe, and this is why we have this descriptive set theory area in set theory, right? Which are the sets we can describe. Then the continuum hypothesis is true for sets we can describe. That's some slogan I'll let to the students to think about. Well, so now I have about 10 minutes to finish the talk. These results as Cantor-Bendixson results, they give lower bounds, right? Uncountable closed set has the continuum below. We change now directions, and the idea is when you give more and more hypotheses on the space, the hypothesis will be separation and countability types, keeping to the basics. The more hypotheses we give, the smaller the space is. So that increasing a hypothesis somehow tame the size of the topological space that's finding. And keep into the basics and the countable or countable related as long as possible. So, for instance, if you have a T1 space, it could be T0, but it's easier to think of T1 spaces. Having a countable base is pretty strong information because this forces the space to have size not larger than the continuum. This first inequality follows from this one. The size of the topology when you have a countable base, the number of open sets, the cardinality of the topology cannot exceed continuum, right? For this later result, the relevant map is going from the subsets of the base to the topology. So for B prime, you go to the union of B prime, which is onto. We are comparing sets with onto, with surjective functions. So we are using the axiom of choice here, right? And for the first result is just to associate to each point the complement of the singleton. You have injection from the space to the topology, right? We weak the countability hypothesis of second to first to first plus third. First and third axiom of countability for metric spaces. This is the same as second countability, right? I'm giving some comments here. I'm going a little faster. Sorry. But, well, a Hausdorff first countable and separable space. So we have the first axiom, the space is first countable, and you have the third axiom, the space is separable. Under Hausdorff, this space cannot exceed the size of continuum, right? This is a nice proof. Well, I'm commenting that for metric spaces, first axiom and third axiom implies the second axiom implies countable base. It's just a trick with the triangle inequality, and this last result does not need of the axiom of choice. You could think that we are doing some countable union of countable sets. No, even without the axiom of choice, we may deal with this. Okay. So the first axiom plus the third axiom for Hausdorff spaces, this ensures that space does not exceed continuum. Here is the sketch of the proof. Fix this countable dense set using the third axiom. For each point, we have a countable subset, which is the image of a countable sequence. I'm a set theorist, so for me, a sequence is a function. So the image of this function, which converge to the point using the first axiom. By uniqueness of limits, this is a map which associates to each point this countable subset of the dense set. It will be injective. So the size of the space would be not larger than the family of all countable subsets of this dense countable set. So it's bounded by the continuum, right? And the same proof gives us something stronger. In fact, using that 2 to LF0 to LF0 equals to 2 to LF0, or countable related case of preference for today. Then the same arguments, you may say that a Hausdorff first countable space that has a dense set which size is not larger than the continuum, then the space is also not larger than the continuum. Well, both presented inequalities are sharp, cannot be strengthened. The real line is a T1 space with a countable base and has size C, and the Sorgen-Frey line, it's a very well-known topological space, is a Hausdorff is countable separable space with size C, right? Well, we could now think if we could drop first or the third axiom. First countability is a local property, so I think it's obvious for everybody that I cannot bound the size of the topological space using a local property, right? I may give as many copies of the space and compute the topological sum and kill upper bounds for cardinality easily. But separability is a global property, so having a countable base, as having a countable base is, so one could think if a Hausdorff separable space would have the size also bounded by the continuum. But no, I may give you the answer. The Stonecheck compactification of the natural numbers as discrete, infinite discrete space. This is beta n. This is a Hausdorff separable space and has size 2 to the continuum, right? This is easy to calculate using ultrafilters, but let's not go there as well. And well, we lost control, the size has grown. There's a sharp inequality for the weakness of sharpness is beta n as well. For Hausdorff separable space, we have precisely this upper bound. The size cannot be larger than 2 to the continuum. Not 2 to the continuum, which is 2 to Aleph 0, right? We are dealing with the power set of a power set. Because of this, we have 2 to Aleph 0, right? There are some hints for the colleague who wants to deduce this. I'm skipping. You may ask for me the slides, or I may give the slides to the organization. To the end, I have to skip some slides, but I have here the map for those who are interested. So Hausdorff separable spaces cannot exceed 2 to the continuum, the size of the subsets of the real line, right? So it seems nice to combine local and global. The more beautiful ways to give these upper bounds to the size of topological spaces would be combining local and global properties. There is a little less easier example. We strengthen Hausdorff to regular, but we weaken the first countability to the property that all points are G delta, right? And we use an arbitrary infinite cardinal kappa just for once in this talk. This is to amuse myself, not other particular reason. But if you have a space with size kappa, with a base of size kappa, you have a base B of size kappa, where kappa is any infinite cardinal, and all points of X are G delta, then the size of X is not larger to the power, which power? The kappa to Aleph 0, right? This would be an upper bound to the size of the set. The size of the base to Aleph 0. Why? Because we are working, I guess if you are accompanying this, you know what to do, right? For any set, we may take a countable subset of the base such that the intersection is the singleton, right? If there's a family of sets, of open sets, we may take a family of basic open sets, right? And with this intersection playing the role of a left inverse, this map, which associates to each point the countable subset of the base whose intersection is a singleton, would be an injective function, so we are done. We have the inequality, right? For us, set theorists, an easy theorem, something we give as exercise to students. And here's the compensation in mathematics. You strengthen in a way, weaken in other way. So we will strengthen Hausdorff to regular, but we will weaken first countable to point G delta. Regular separable space without point G delta has cardinality not larger than the continuum. And these follow by the regular open sets being a base for any regular space, right? There's the definition. And if you have any, here should be dense set. There's a typo. If there is any dense set of a topological space, then the family of our regular open set would be the interior of the closures of subsets of this dense set. This should be dense set. I have to correct this typo. Right? I will have no time to discuss the main result. The main result comes from a problem from the 20s of the 20th century. Alexandrov and Urison have shown that compact, perfectly normal Hausdorff spaces have size not larger than the continuum. Then the problem them will be if compact first countable Hausdorff space should have cardinality bounded by continuum as well. And the solution of this problem was given in the 60s by Arangelsky. It's still alive, it's still working. The countable Arangelsky theorem is that Hausdorff first countable Lindelof spaces cannot exceed the size of the real line. And in fact, the proved theorem was the general theorem, which is in terms of cardinal functions, that for Hausdorff spaces, then the size of the space is not larger than 2 to the Lindelof degree times the character, right? And I will not be able to give a proof, not even if I run here. I guess it's better to send the slides for interested people. This is a proof which uses the closing off argument. Is a method to Poe and Sapirowski in the 70s. And the interesting thing is that this Poe-Sapirowski technique is nowadays being done using elementary submodels. It's doing Lovenheim-Skolin type arguments, right? So I have to skip, I'm sorry. And a few remarks. This closing off process is nowadays using logic arguments. All arguments are put under the rug, right? As Polish spaces are separable in metrics, so they are Lindelof. So you have, together with Cantor-Bendixson, precisely the size of the continuum with both inequalities. And we have some. This third observation I will skip because it's subtleness we have with the compact case and the Lindelof case. So there are forcing constructions that are maybe would surprise some people. There is this Goralick construction of Lindelof space with point G delta whose size is larger than continuum, because this point G delta and the first countability are not equivalent conditions in general. And just to end with the talk, these Santi Spadaro and Leandro Aurici, these are younger mathematicians, around 40 years of age. They work with the senior researcher Angelo Bella, Italian. The technique, besides of elementary submodels, these guys usually obtain several inequalities for the size of topological spaces using topological games. There are several games between two players, infinite games with infinite uncountable number of rounds, right? And when player 2 has a winning strategy, then you can show that there is a limitation in the size of the topological space in terms of cardinal functions. So I'm sorry that I couldn't present the proof of Arangelsky theorem, but I guess the basic proof are interesting as well. And I hope see you all in Salvador as soon as possible. We are always receiving people. We have this logic sets and topology group at Salvador, Bahia, Brazil. So you're all invited to come and visit us. Thank you very much.
¿Alguna pregunta de parte del público? Cristian Calderón, ya, en breve le van a permitir para que le van a activar para que haga su respectiva pregunta.
Sí. Y perdón por el tiempo. Esa es una charla nueva, todavía no estoy de control del tiempo. Creí que iba a poder hablar en una hora, pero no.
¿Qué tal? Buenas tardes con todos. Hi,
Buenas
Samuel. I'm
tardes.
Christian.
No,
I think I'm
puedes preguntar en castellano. Creo que para platicar así en castellano voy a poder.
Perfecto, perfecto. Samuel, soy un estudiante de grado de matemáticas aquí de Ecuador. Me pareció interesante,
Sí, sí,
bastante, y más que
sí, sí.
nada respecto a la bibliografía, cuando mencionaste que uno encuentra libros, pero más que nada los libros asumen que uno ya sabe algo sobre.
Sí, sí, sí.
¿Habrá bibliografía en la que uno como estudiante de grado, siendo tan chiquito, tan
Ujú.
ignorante en varias cosas, habrá algunos libros a los que uno se pueda referir o profesores o
Ujú.
lecturers de algunas otras universidades de las que uno pueda leer
Ujú.
para introducirse al tema?
Bueno, he mencionado a ese Leandro Auric, ¿no? Leandro Auric trabaja en la Universidad de São Paulo en São Carlos, ¿sí? A la ciudad de São Carlos. Y este Leandro Auric es una persona muy moderna, entonces tiene sus notas de clase en su página, tiene muchos videos en YouTube, incluso han creado, con los estudiantes, han creado un seminario de cosas buenas, ¿no? En portugués es un chiste, es es decir, seminario de cosas chéveres, así, en portugués es seminario de cosas legais, cosas chéveres, cosas buenas, así, y muchos estudiantes presentan. Entonces, así de memoria, para empezar, creo que, bueno, está en portugués, pero creo que se puede manejar, ¿no? Creo que es una buena introducción a eso de aplicaciones de conjuntos en topología, porque si usted tiene un curso con Leandro, si usted tiene un curso conmigo, si usted tiene un curso con Lúcia Junqueira, la topología va a aparecer impregnada de teoría de conjuntos, ¿no? Entonces es mucho más una manera de ver la topología, no es tan geométrica, ¿no? No estamos más interesados en los tamaños de las familias, de cosas y todo, ¿sí? Y bueno, puedes me escribir siempre también, estoy siempre en contacto con estudiantes, ¿sí? Sería eso.
Muchas gracias, profesor. Tenga buen día.
¿Alguien más que quiera formular su pregunta? Bueno, en vista de que no hay más preguntas, vamos a... Muchas gracias, doctor Samuel Gómez. Vamos a presentar su certificado en este momento.
Muchas gracias.
Ahí voy a compartir. Bien. La Universidad Nacional Mayor de San Marcos, Facultad de Ciencias Matemáticas, en el cuarto Congreso Internacional de Topología y Afines, otorga al doctor Samuel Gómez da Silva, en mérito a su participación como ponente, el siguiente certificado, lo cual le estaremos haciendo llegar a su correo electrónico en los días sucesivos. Muchas gracias.
Bien. Muy bien.
Muchas gracias, doctor.
Gracias, gracias, Kevin.
Contar con usted en los próximos eventos. Gracias.
Un saludo, gracias.